So today I want to start chapter 9, which is about differential equations. We will only do 9, 1, 9, 3. That's all what we're required to do from this section. So today let's go over 9, 1, which is about modeling with differential equations. So mostly what we're going to do in section 9.1 is what exactly is a differential equation and what makes a solution to the differential equation. Okay, and just as an introduction, many of the principles in science and engineering concern relationship between changing quantities. Since rates of change are represented mathematically by derivatives, such principles often the equations involving unknown functions and their derivatives. So from real life, you get some models that can be transformed into equations that have the function and the first derivative or the second derivative and so on. In this section, we'll talk about solving differential equations. Before we get to solving differential equations, we'll understand what a differential equation is, what a solution is, and how to solve it is going to be mainly in 9.3. And also in this section, we'll just see some application about exponential growth and decay models. So what is a differential equation? Just from the word, differential means has derivative. Equation, of course, it has an equal sign, is an equation involving one or more derivative of an unknown function y equals f of x. So it involves y prime, y double prime, and so on. What exactly is the order? So when we say the order of the differential equation, the order of a differential equation is the order of the highest derivative it contains. So if the highest derivative is third derivative, you look at the order. Is it to the first excuse me, is it to the first power, to the second power, so on. For example, dy by dx equals 3y. This is a differential equation. It has the derivative y prime equals 3y. Its order is 1. Why order is 1? Because y by dx, which is y prime, has a power of 1. Okay? Now if you look at d2y by dx squared equals negative 6 dy over dx plus 8y. Again, the order here is 2 because the highest derivative is 2. Okay, highest derivative is 2. Second derivative. Okay, so what exactly is a solution? A function y equals f of x is a solution of a differential equation if the equation is satisfied. So meaning if you plug in that value into the equation, you get a true statement for all x in some interval when y and its derivatives are plugged in. When y and its derivatives are plugged in. So if you're checking if y equals f of x is a solution and the equation, the differential equation has y prime, then you gotta also plug the value of y prime in there. That's what it's about. And if you plug y and its derivatives into the equation and you get a true statement, then it's a solution. If you get a false statement, then it's not a solution. So is y equals e to the 2x a solution of dy by dx minus y equals e to the 2x. Well, let's see. We got y. What's dy by dx? The derivative of e to the 2x is e to the 2x times 2. So if we put in there 2e to the 2x minus y is to the 2x, that equals e to the 2x, which equals that. So it is a solution. Number 10, page 610 from your textbook. Again, they give us y equals square root of 1 minus x squared and y prime minus x equals 0. So is y a solution of this equation? Well, before we do that, we want to find y prime. So y prime is u prime over 2 square root of u, so it's negative 2x over 2 square root of 1 minus x squared, which is negative x over square root of 1 minus x squared. So we put that in there. Y is square root of 1 minus x squared times y prime is negative x over square root of 1 minus x squared. X equals 0. Negative 2x does not equal 0. It does only when x is 0, but this has to be true all the time, so it's not a solution. Differential equations sometimes have what we call initial conditions. What exactly is an initial condition of a differential equation? So for a first order differential equation, a condition that satisfies the value of the unknown, function y equals f of x at some value x equals x0 is called an initial condition. So, for example, if you have, say, y minus y prime plus 2x equals 0, and then y of 0 equals 2, for instance, this is called initial condition. It's a initial condition that satisfies the value of the unknown at some value of x. So at x equals 0, y of 0 equals 2. Okay, that's called an initial condition. Now, a first order differential equation, the one that has a y prime, together with its initial condition, with one initial condition, constitutes a first order differential, a first order initial value problem. So when they say a first initial value problem, it means we have a first order differential equation with an initial value. First order differential equation with an initial value. So number 14 from page 611. It says, show that the given function is a solution of the initial value problem. So here's the initial value problem, y. Here's the one that we should show it's a solution. 5 equals e to the 2x plus x, and the differential equation is dy by dx minus 2y is 1 minus 2x, and the initial value is, or initial condition is, y of 0 equals 5. You can see, like, if you put a 0 for x, e to the 0 is 1, 5 times 1 is 5 plus 0 is 5. So that the initial condition has to always satisfy the solution, okay, of that equation. So if for that to be a solution, it does satisfy that, and then this has to be, when you plug it in, it has to be the true statement. So dy by dx is 5 times 2, which is 10 e to the 2x. So if you put that in here, 10 e to the 2x minus 2y is 2 times y is all that. It should equal 1 minus 2x. So distribute 10 e to the 2x minus 10 e to the 2x minus 2x. Well, I think I left out something. Y prime is 10 e to the 2x plus 1. Okay. Don't forget the derivative of x is 1. So 10 e to the 2x plus 1 plus 1. So you get 1 minus 2x equals 1 minus 2x. So that's true, and also we already checked that y of 0 is 5. You plug it in there, so we have a solution. Okay. Now, as an application of the differential equations is what we call growth and decay problems. Growth and decay model. So it could be, it could be money in a bank for growth, population size, or it could be radioactive substances for decay problems. So if P is a differentiable function, of time t, like population size or principal of money that you borrow or invest in a bank account, such that, of course, P is positive, and dP by dt is Kp. What you can see, the rate of change of that principal or population with time is directly proportional to the population itself. K is called variation constant. Then P is C e to the Kd, where C, P of 0 equals C, as you can see. If you put a 0 for T, e to 0 is 1, so C is P of 0. That's your initial condition. So basically what we're saying here is solution for the growth or decay. If K is positive, you have growth, and if K is negative, you have decay. Okay, K is positive, it's growth, and K is negative, decay. And I proved that in the notes, so you can look at the proof. It's very simple. Okay. But anyways, so I just wanted to show you where this formula came from. So a solution for the differential equation, first order differential equation, is this one, P equals C to the KT. And it looks like paired, if you remember. Okay, it looks like paired. So if you look at number 2, page 610, it says, write a differential equation that models the given situation. In each case, this rate of change is with respect to time. The rate of change of the velocity of a falling body is constant. So the rate of change of the velocity is constant. So we just put C where C is constant. That's all we have to do here. Okay? So simple stuff. Now, more on population growth, which is really important. Because, especially if it's a population, it reaches a certain limit. Population size is usually increases, but then it reaches a certain limit and it starts coming down. So they start leveling off. So many populations start to level off when it approaches, when it's approaching its carrying capacity M. Okay, so if the carrying capacity is M, many populations start to level off when it's approaching its carrying capacity M, or decreases toward M if it ever exceeds M. So it reaches its carrying capacity. Sometimes it goes a little bit over it and then comes down. Other times it never reaches that, then it comes down. Okay, so to take that into account, that capacity, we know that dp by dt is kp. We talked about this, we already did, right? If so, it's kp, and dp by dt is negative if p is greater than m. So once you reach that carrying capacity, then the rate of change becomes negative, so the population decreases, b decreases if it ever exceeds m. So dp by dt equals kp to 1 minus p over m, where k equals cm. This is what they call logistic differential equation. So look at this. If p is the population is small compared to m, if p is relatively small compared to m, so p over m actually goes to 0, and we go back to the case where p is, where the original case where there's no carrying capacity. Okay, if p is greater than m, then you can see that dp by dt is negative, and that means population is decreasing. Okay, population. So that's what we're talking about, and that model represents the population growth and decay. It's so if the population size is less than m, then you're okay, the rate of change is increasing. If it's greater than m, then that's going to be negative and it's decreasing. So let's look at a few more examples. Number 4, page 610. It says, when an infectious disease is introduced into a city of fixed population n, the rate of change of the number y of infected individuals is proportional to the product of the number of infected individuals and the number of non-infected individuals. So when an infectious disease is introduced into a city of fixed population and the rate of change of the number of the rate of change of y of the number of infected individuals, so dy by dt, is proportional to the product of the number of infected individuals, ky, y is the number of infected individuals, and the number of non-infected individuals. What is the number of non-infected individuals? It's n minus y, right? Because n is the population size and y is the number of infected, so n minus y would be the number of non-infected. Individuals. Because n is the population size and y are the infected, so population size minus the infected gives you the non-infected, and that's directly proportional to the number infected and the number of non-infected, and they all want to. So this is similar to the what we were talking about. Okay, the kp 1 minus p over n, sort of thing. Okay, number 20, page 611. Number 20, page 611. What can you say about the graph of a solution? What can you say about the graph of a solution of the equation y prime equals xy cubed? when x is close to 0, so this is part A, and when x is large. So what can you say about the graph of this when x, so first if x is 0, is close to 0, that means y prime is close to 0, right? 0 times y cubed, which means the graph has a horizontal tangent line. We know that from basic algebra, so graph has a horizontal tangent line. So nothing fancy here. What if x is large? If x is large, that means y prime is large, right? That means y prime is large. And if y prime is large, the slope is extremely large, so the graph has near vertical tangent line. The graph has a near vertical tangent line, because tangent lines that are vertical have extremely large slope, you know, it's undefined or infinity. Okay, so y prime is very large. Part B, it says verify that all members of the family y equals c minus x squared to the negative 1/2 are solutions of differential equation y prime equals x cubed. So let's do that. So if this is y, then y prime is negative 1/2 c minus x squared to the negative 3/2 times negative 2x. The derivative of c minus x squared is negative 2x. That cancels that out. Y prime is x times c minus x squared to the negative 3/2. So go back here, y prime equals xy cubed, x times c minus x squared to the negative 3/2. Does that equal x times c minus x squared to the negative 1/2 cube? You can see it is c minus x squared. Negative 1/2 times 3 is negative 3/2. Okay? And then part C, it says graph several members of the family solutions on a common screen. You can use your grapher to do that. Use grapher. Like here, what they want you to do is put in a value for the constant. Put 1, 2, 3, and see what happens with the graph. That's what they want you to do. So I want you to explore that. And that ends section 9.1.